testing, I'll go over the definition of what insulation actually is, which most of you probably already know. The concept overview, a brief introduction to some of the theory behind how they measure it, the measurement devices used to measure insulation, and some applications. Definition is pretty straightforward. It stems from incoming solar radiation, which is how they come up with insulation. It's a long acronym, but it's one that's pretty useful. And it's basically a measure of the intensity of incoming solar radiation on an object located on the Earth. This is a visual representation of solar insolation. This is during the January through May, June, July months, and this is July through December. You can see the intensity ranges based on which side of the equator you lie on, and that's how we actually get our seasonal flips. So in the wintertime, when you want a vacation, you head south on the northern hemisphere, but it's the opposite for the southern hemisphere. Brief overview of insolation. It is the main source of energy on our planet. It determines seasonal variations in the temperatures that we experience. It depends on multiple factors. A lot of people thought that seasonal differences was due to the distance between the Earth and the Sun. It actually depends on more than just that. The time of year and time of day are obviously pretty crucial depending on your location. But the solar declination is very important, and we'll get into that a little bit later. The distance does have some effect, but it's a lot smaller than some of the other factors, such as atmospheric conditions, but mainly your latitude location. The latitude effects are the main effect of solar insolation, how much you perceive. It decreases with an increase in latitude due to the Earth's tilt. It's actually tilted about 23 degrees. This graph kind of represents different latitudinal locations on the Earth and how much solar insolation they actually receive when you're directly across, like on the equator. You typically get upwards to 100% of the insolation from the sun. But as you move further, either north or south from the equator lines, the percentages decrease. And this is due to the Lambert's cosine law, where it actually gives you the percent of the incident solar radiation you'll experience due to your latitude location. This theta is the solar zeta, where it's a little bit tricky to explain, but it's the angle in which the sun contacts the perpendicular location you are on the Earth. It's determined by using your observer latitude and the solar declination factors. Some measurement devices used to measure insolation. There are a couple. The pyranometer is real expensive to use. It measures the total global radiation. As you can see, there's a hemispherical collection device on the top in which it collects the insolation from all of the surrounding environment and then calculates it. The pyrahelium, I cannot pronounce this to save my life. Pyraheliumeter? Y'all have better guesses at saying it. I'm with you on it. It measures direct radiation. It's a little bit less accurate as it only has a 5-degree acceptance angle of the sunlight getting through the device. It does have a 2-axis tracking mechanism which can move with the sunlight to measure it at different times during the day. And the most basic form is the Campbell-Stokes recorders, which are sunshine recorders. It basically just measures the amount of sunshine that it receives throughout the day. It's very inaccurate because it only works when it's super bright in the visible range. So if you have a sun in a low position or it's super cloudy out and there's a lot of atmospheric effects, it doesn't calculate it as accurately as one of these two devices, but they're very cheap. So that's our main source of measurement. Some common engineering applications of understanding insolation and using these measurements. First and foremost is spacecraft design. They affect the equilibrium temperature of the spacecraft, so they try and utilize that to maximize it while we have astronauts in space. For architectural purposes, they like to optimize human comfort in buildings. This is kind of one of those that I didn't actually think of right away. when I was researching this, they actually take insulation graphs, kind of like the first slide I showed you, based off the latitude in which the building is located, and they manufacture large windows which face the equator. Depending on which side of the equator you're on, it'll face the south or the north. In this way, it maximizes the insulation that the building absorbs during the winter months and minimizes it during the summer. So it helps with the efficiency of heating and cooling the building. It's used in solar panel systems to calculate the panel output that it will receive and size the panels based on the location. This is done by measuring the angle of declination and where it is latitudinally located to optimize which angle it should be adjusted to collect the most radiation that it can. It is also used in civil engineering applications. It's used to model different snow melts for the mountains or different regions that experience a lot of ice. So they can calculate how much runoff they may experience in the area for different roadway purposes, building bridges, to eliminate the chances of flooding for residents. So that was kind of interesting. Any questions?
So if it wasn't so cold up north or way down south, and you decide to go all naked, you wouldn't get sunburned because you're not getting any solar radiation? Yes, my mind works in mysterious ways. Isn't it?
A little bit. It's a little strange. I don't think I'd ever catch myself running around naked on one of the bowls. It's kind of different. It's a lofty goal, I think. Honestly, insulation is more so how much thermal radiation an object receives from the sun. So I think that you could still probably get burned. Honestly, I'm not sure. I haven't really been that far north. I live north, but not that far. I get sunburned in winter a lot back home, actually, because you don't think about it, but you're still receiving a lot of radiation rays, I guess, not so much the heat from it, but.
But that's still like in the 60% range. So
True.
you're up at the 0%.